Hey everyone, welcome back. This is lesson 3 in our unit 5 stoichiometry, and today's lesson is called determining missing pieces in a reaction. So, in the last video, we talked about the different types of reactions, the synthesis, decomp, single replacement, double replacement. There are more, and we'll get to them when we get to organic chemistry, but for right now, those are the 4 that you need to know. So again, on this episode, we're going to kind of review conservation of mass pretty quickly and kind of apply that question to how to determine missing pieces within a reaction. So remember from our balancing video, conservation of mass says nothing can be created or destroyed during chemical reaction. So what you start with is what you end with. It's just rearranged in a different manner. So if you have this airplane, you have, the pieces and they all come together to form the airplane. You didn't magically, lose that. You didn't magically grow, I don't know, more things. What you start with is what you end with. And that's what the conservation of mass is. What you start with is what you end with. So the total mass of the reactant, so the stuff you're starting with, equals the total mass of the products, what you end with. And then if we know we can't create or destroy stuff, we know that the number of each thing should be the same number as at the end. And that's, again, why we balance equations. So if there are 2 types of questions here, and we'll cover both of them. We'll go through an example of 2 examples of each of them. So first, if we're going to determine the unknown reactants or products. So this is if I give you a chemical equation and I pull out one of the compounds, you should be able to figure out what is missing. And so here are your steps. And so we'll go through this together. But we're basically solving for x. And there is a difference between x and 2x. There is also some 3x's. And we'll go through examples with this so you know what I'm talking about. So here is a chemical reaction. 2 Na plus 2 waters gives us x and 2 NaOHs. Our job is to figure out what x is. So our steps was to list out what we have and then figure out what we're missing. So we have NaHO. You're kind of starting off as if you were balancing an equation. So we have 2 Na's, we have 4 H's. Remember, the big 2 goes to the entire thing. We have 4 H's and we have 2 O's. And then at the end, based on what we're given, remember 2 goes to all of it. We have 2 Na's, we have 2 hydrogens, and we have 2 oxygens. So what are we missing here? Our Na's are good, our O's are good, but we're missing 2 hydrogens. And so our x is equal to 2 hydrogens. And so we say x is H2. So then if we plug H2 into our equation, be right over, 2Na plus 2H2O gives us H2 plus 2NaOH. So H2 is that missing piece. Now, X means there's one of them. So that's the coefficient. We just have to make a compound using those things. So X will give you the pieces that the compound needs to be made out of. So we need to make a compound out of 2 H's, and so that is H2. Okay, so let's try another one. And this is what I was talking about before. We have 2X. So let's list what we have. We have Fe, we have O. So we're starting with 4 H's and we're starting with 6 O's. Remember, this goes to that. And then we're ending with FeO. We're ending with nothing. So we are missing 4 Fe's and 6 O's. So we have 2X. So we have 2 of these compounds. So that means 2X is 4 Fe and 6 O's. But we just want to figure out what that 1X is, so you divide both things by 2. So X is 2 irons and 3 oxygens. So those are the pieces of the compound. So you have to make a compound with 2 Fe's and 3 O's. So X is Fe2O3. And that is it. So that 2 is helps us bring down and get the actual formula. So that would be it. So then our final equation, if you were to rewrite this, you don't have to, would be 4Fe plus 3O2 gives us 2 Fe2O3. And then if you were to check it, everything is balanced. So most of these questions are multiple choice, so you're able just to really count what you're missing. And you'll see practice with that as well. But that's that. Again, just taking it step by step by step. If you're ever confused, rewatch these videos again and again and again, because they all work the same way. Okay, so this is kind of maybe the easier part of it. If we're giving you masses of things, you're able to kind of figure out what the missing mass is, because again, what you're starting with is equal to what you're ending with. Now, sometimes they'll give you word equations and word stuff, and it doesn't matter if you can figure out the formula of a compound. That's not what's important. What's important is knowing what's a product and what's a reactant. So what's on either side of the equation. Okay, so here we have the question. If 103 grams of potassium chloride are decomposed to form 62.7 grams of potassium chloride, an oxygen gas, according to the equation how many grams of oxygen are formed? So they give you the names of the stuff, of the compounds, and they give you the formulas. Again, it's not super important that you know what's what. It is to a point, but as long as you can know what's a reactant, what's a product. So potassium chloride are decomposed to form. So everything after the word form, remember those are your products. So potassium chloride, well that's this, is 62.7 grams. Plus oxygen, it didn't tell us what that was, and it told us we were starting with 103 grams of KCl3. So again, words, the compounds aren't that important as long as you know what's a reactant, what's a product. And so, due to the conservation of mass, you know the mass of what you start with has to equal the mass of what you end with. So, the mass of the reactants has to equal the mass of the products. So then you give yourself a very simple algebraic equation. Let's solve for x. So we just subtract both sides by 62.7, and you get 40.3 equals x. So that's your answer. That's it. 40.3 grams of O2. So you might have been thinking, oh, darn, I need to, convert to moles. I need this, I need that. Nope. That's it. Everything is given in the question. The trickiest part, though, is putting the number correct next to the next correct compound. Okay, so let's do one more of these together. How many grams of silver nitrate are needed to react with 156.2 grams sodium sulfide to produce 595.8 grams of silver sulfide and 340 grams of sodium nitrate? Okay, so here we're not given formulas at all, but we can still kind of come up with a formula. So we have silver nitrate plus sodium sulfide are needed to react with. So that means we're starting with this and we're ending with everything else. So we're starting with silver nitrate and sodium sulfide, and we're making silver sulfide and sodium nitrate. So again, that is our formula. We don't need to know formulas. We just need to know what's a reactant and what's a product. So we are not given the mass of this. That's what we're looking for. But the question says we have 156.2 grams of sodium sulfide. We know that the mass of the reactants is the same as the product, so we can use that equal sign. Question says 595.8 grams of silver sulfide and 340 grams of sodium nitrate. So all of that came from the question, and now we're left solving for x. Again, here is your simpler-ish algebraic equation. So you get x plus 156.2 is 935.8 minus 156 on both sides. 2. So you get x is equal to 779.6 grams of silver nitrate. Again, as long as you know before the arrow equals end of the arrow, that's all you need to know. So again, we're going to practice with this for some time in class. Again, watch these videos as much as you need. They all work the same way. So once you get the kind of routine in your head, then questions will be easier to do. Next time, we will cover mole ratios. On that note, have a wonderful day. Bye.